Welcome! Today we're going to build a powerful toolkit for one of the coolest applications of calculus, optimization. We're going to turn what might look like a super complex, intimidating problem into a simple, repeatable strategy you can use every single time.
Okay, let's dive right in. Before we even touch a single number, we need to get our core game plan down. This is a universal strategy, and believe me, it works every single time, even when the math starts to look a little messy.
And here's why this is so important. Optimization is literally everywhere. From figuring out the cheapest way to make packaging to finding the absolute fastest route somewhere. The math might get wild, but the strategy, it stays the same. That's the whole challenge and the promise of this. Finding the absolute best outcome. The cheapest, the fastest, the strongest. And the good news is, there's a universal toolkit for it.
So, it all boils down to this simple three-step process. First up, step 1, you find the constraint. This is basically the rule of the game, the thing that limits you, like a fixed budget or a set volume. Then, step 2, you identify the primary equation. This is your goal, what you actually want to maximize or minimize. And finally, step 3, you optimize. You use that constraint to rewrite your primary equation so it only has one variable, then you find its derivative, set it to 0, and solve. That's it. Constraint, primary, optimize.
All right, theory's great, but let's see this toolkit in action, right? Let's get our hands dirty with our first case study. This is a classic distance problem you will definitely see in a calculus course. So here's the scenario. We've got a parabola defined by x equals 1/2 y squared, and we've got this point just kind of hanging out at 1, 4. Our job is to find the exact point on that curve that is the shortest possible distance away from our point. You can almost picture it, right? Drawing a line from the point to the curve, we want to find where that line is the shortest.
Okay, so our first instinct, naturally, is to whip out the good old distance formula. And hey, it's not wrong, but you see that giant square root symbol? You can probably guess what that means. Taking the derivative of something with a square root involves a messy chain rule, and that's exactly where mistakes happen. We can do better.
And this right here, this is the pro tip that changes everything. Instead of minimizing the distance, d, we can just minimize the square of the distance, d squared. Think about it for a second. If a distance d is as small as it can possibly get, then d squared is also going to be at its minimum, because distance is always positive. This one simple trick lets us ditch that nasty square root, which makes the derivative a breeze, and it gives us the exact same final answer. It's a total game changer. And boom, here's the power of that tip in action. We've taken our d squared formula and just plugged in the parabola's equation for x. What we're left with is this much cleaner function of y. Look at that. It's just a polynomial, which is way easier to differentiate. Now, we just follow the process. We take the derivative of our new function, which, after a little bit of algebra, simplifies really nicely to just y cubed minus 8. Then, we set that derivative to 0. Remember, finding where the derivative, or the slope, is 0 is how we find those potential minimums and maximums, those flat spots on the graph. A quick solve here, and it's clear. Y has to be 2. The last step is a piece of cake. We just need the x-coordinate that goes with our y. So we plug our solution, y equals 2, back into the original parabola equation. So x equals 2 squared over 2, which is just 2. And there we have it. The point 2, 2 is the closest point on that parabola to 1, 4. Done. Awesome. Now that we've walked through the technique step by step, let's see how our universal toolkit applies to some totally different scenarios. The key here, and this is really the trickiest part of these problems, is just getting the setup right. First up, a classic engineering problem you see all the time, designing a can. The goal is to hold a very specific volume, 1,000 cubic centimeters, but we want to do it using the least amount of material possible. And that, of course, means we need to minimize the surface area. So, let's apply our strategy. What's the constraint? Well, it's that fixed volume. The formula for the volume of a cylinder, pi times r squared times h, absolutely must equal 1,000. And what's our primary equation? That's the surface area, the thing we want to minimize. The formula for that is 2 pi r squared plus 2 pi r h. Now for step 3. We use our constraint to get everything down to one variable. The easiest way is to solve that volume equation for h. That gives us h equals 1,000 divided by pi r squared. Now we can substitute that into our area formula. We're left with the new primary equation for area that only depends on the radius, r. From there, it's the same old story. Take the derivative, set it to 0, solve. And when you run the numbers, you find the solution. The most efficient radius is about 5.42 centimeters.
Okay, let's level this up again with a super fun pathfinding problem. It's all about minimizing time. So we've got a dog who can run way faster than it can swim. There's a ball 20 meters down the shore and 10 meters out in the water. The big question is, where should the dog jump in to get to that ball as fast as possible?
So our primary equation here is total time. And remember the basic physics. Time equals distance divided by speed. So the total time is going to be the time the dog spends running on the shore plus the time it spends swimming in the water. Simple as that. So how do we even set this up? Well, let's call x the distance the dog runs along the shore. Now the tricky part is the swimming distance. It's actually the hypotenuse of a right triangle. The sides of that triangle are the 10 meters out from the shore and the rest of the shore distance, which is 20 minus x. A little Pythagorean theorem tells us that swimming distance is the square root of 10 squared plus 20 minus x squared. We plug those distances into our time formula, take the derivative with respect to x, set it to 0, and solve. And the math shows the dog should run about 17.9 meters down the shore. It makes sense, right? It wants to spend as much time as possible at its faster running speed.
So, after looking at closest points, soda cans, and even a dog fetching a ball, what's the big picture here? Let's bring it all home.
Just remember, no matter how wild or complicated the problem looks, it always comes back to this same three-step strategy. Step 1, find your constraint. That's the rule you can't break. Step 2, define your primary goal, the thing you're trying to perfect. And step 3, use that constraint to simplify your goal. Then let calculus do the heavy lifting to find the optimal point. It really is that reliable.
And you know, this isn't just about getting a good grade on your next exam. This is a really powerful way of thinking about efficiency and finding the best way to do things out in the real world. So the final question is for you. Now that you have the toolkit, what will you optimize? Thanks for joining this explainer.